Alright, so before we move on to the next example, here's a warning. Finding a Jordan normal form is hard, very hard in general, because it's complicated to find chains of generalized eigenvectors. So we're going to stick with small examples. So let's consider x prime is equal to 1, 0, 0, 1, 3, 1, negative 2, negative 4, negative 1, x. Let's call this A. Then standard procedure, characteristic equation, determinants of a minus lambda I equal to 0. So this equal to 0. First row has a lot of zeros. Let's do that. This is a plus. So 1 minus lambda times the determinant of a smaller one. 3 minus lambda 1, negative 4, negative 1 minus lambda equal to 0. 1 minus lambda. And this is 3 minus lambda, negative 1 minus lambda, minus 1 times negative 4 equal to 0. So 1 minus lambda, lambda squared, minus 2 lambda, minus 3 plus 4, so plus 1 equal to 0. So this gives you negative lambda minus 1 cubed equal to 0. So lambda y equal to 1 is the only eigenvalue, and the multiplicity is 3. Alright, so that's the eigenvalue. We want eigenvalue, so let's now move on to solve a minus lambda I, so a minus I times v equal to 0. So this gives you 0, 0, 0, 1, 2, 1, negative 2, negative 4, negative 2 times v equal to 0. The first row tells you nothing. The third row tells you the exact same thing as the second row. So this thing has got only one row that tells you information, which means there's two free variables. So the solution are, if you let the last one v3 to be the free variable, then v1 is going to be negative 1, v2 is going to be 0. If you let v2 to be the free variable, then v1 is negative 2, v3 is 0. So these two are linearly independent solutions to this equation. So if you draw the diagram for the chain of eigenvalues, then we have negative 1, 0, 1 goes to 0 if you multiply it by a minus I. And we have negative 2, 1, 0, it also goes to 0 if you multiply by a minus I. So now the problem is how we're going to determine. So this means two eigenvectors. So this means our eigenvalue is defective, which means, and a defect is 3 minus 2, which is 1. So that means the diagrams of generalized eigenvectors should have a chain with length 1. So this means we have two chains. One of length 2 and another one of length 1. So we need to manually create a chain of length 2. So the way to do is we're going to start with a random vector, which this is literally a random guess. 1, 0, 0 is the most convenient guess. It might not work, but in most of the cases it's going to work, so we're going to stick with that. So we're going to see where it goes. So a minus I is 1, 0, 0, 0, 0, 1, 2, 1, negative 4, negative 2, negative 4, negative 2. We're going to multiply this by 1, 0, 0. So this is equal to 0, 1, negative 2. And then if you multiply by a minus I again, 0, 0, 0, 1, 2, 1, negative 2, negative 4, negative 2, times 0, 1, negative 2. This is going to be 0, 0, 0, which is a 0 vector. So this is the length 2 chain we need. So this is going to be our V1, and this is going to be our V2. So we have a chain of length 2. All we need is another chain of length 1, and we have two candidates here on top. There's this one or this one. Both of them are part of the chain with length 1. So the secret is either of them can be V3. Just to be careful, we need V3 to be linearly independent from V1. So because it's just one vector, so all we need to do is to make sure that V3 is not parallel to V1. And in this case, neither of them is parallel to V1, so we can choose either one to be V3. So we're just going to choose the first one to be convenient. It's fine if we choose the second one, that's alright. Alright, so we have our V1, V2, and V3 ready. So A, our matrix can be written as the Jordan normal form. So P is the matrix with V1 being the first column, V2 being the second column, and V3 being the third column. In the Jordan form, the diagonal is the eigenvalue, which is 1, 1, 1. This is going to be mostly 0. So because V2 has an arrow going to V1, so this entry is 1. This is telling you that V2 has an arrow going to V1. And then this entry is 0 because V3 itself is an eigenvector, so we don't need, it's not pointing to V2, so this entry is 0. So that's our Jordan normal form for A. And the generalized solution for the differential equation is x equal to, so there V1 is an eigenvector, so it gives you C1 times e to the lambda t. Lambda is 1, so it's e to the t times V1. And V2 is pointing to V1, so we have the terms piling up. So we have C2 e to the t, V2 plus TV1. And V3 itself is an eigenvector, so it's by itself, so it's C3 times e to the t times V3. So the first two terms refer to this part, and the third term is V3 by itself. And if we really want to write it in a scalar form, we can do that. So it's three equations, x1, x2, and x3. Okay, so let's write this out first. So C1 e to the t times V1, which is 0, 1, negative 2, plus C2 e to the t. V2 is 1, 0, 0. T times V1 is 0, 1, negative 2. And C3 to the t. V3 is negative 1, 0, 1. So the generalized solution in scalar form is x1 equals to, there's no C1, plus C2 e to the t times 1 plus C3 times e to the t times negative 1. So that's x1, and x2 is the second coordinate, which is C1 e to the t times 1, technically, plus C2 e to the t, 0 plus t, and there's no C3. And x3 is C1 times e to the t times negative 2, plus C2 e to the t, negative 2t, and plus C3 e to the t times 1. So this is the general solution in a scalar form.